All right, how is everybody doing? The Canadian listeners, I hope you guys had a good Thanksgiving. All right, so let's start now. So as usual, just if you have any questions, put them in the chat or just speak up, because in case I'm not paying attention to the chat. So two announcements. So I have posted a problem set in the Slack. It's not particularly difficult. There might be a couple of parts which are more difficult than the rest, but the rest should be straightforward. So try it. And the other thing I posted in the chat is that the November 4 to 7, we're hosting a workshop in optimal transport at the Fields Institute in Toronto. If you, I mean, this take it as a part of the course, attend it, register for this workshop, attend as many talks that you can. It will give you a flavor of the kind of current research that goes in the field. Okay. And let's see, there is a question here. Okay, so from the current class, from the last class, can you explain why the geodesic convexity of those three classes of functionals are helpful? What is the applications of that is? Yes, so that's exactly where the gradient flow will come into this. So one of the big applications, at least in my mind, I mean, I'm a probabilist, so I only care about the statistical applications much more, is in the theory of sampling. If you want to sample from some sort particular distributions, you create some Markov chains or a diffusion or some discretization of diffusions to sample from a certain distribution. This is one of the big problems in machine learning or artificial intelligence. Um, the traditional way of studying these diffusions, means that you want to understand the rate of convergence of these diffusions or how well they behave in practice, they have been more probabilistic based, more probabilistic ways of understanding. As we will see when we do gradient flows, that optimal transport gives an entirely geometric way of understanding the rate of convergences of these diffusions. And this is often very useful. And this is one of the main reasons why we want to study gradient flows. Now, when you study these diffusions, you want to understand what is the rate of convergence. One particular the distance that comes up, or rather not a distance, is divergence, is a Kullback-Leibler divergence. This is, if you're coming from statistics background, I don't need to convince you that this is a very important notion. And many of the convergences are based on Kullback-Leibler divergence. And therefore, this is where the convexity of the Kullback-Leibler or entropy kind of object becomes very crucial. This is only the statistical applications. There are many, many other reasons entropy and Kullback-Leibler divergence are fundamental objects in statistics or in physics. And there are many reasons why those particular functions are very important. Does this give a good enough reason? But these are coming. All right, okay, good. Let's start. So let's start with today's class. So we're going to talk about, now we're going to start talking about this metric space theory of the Wasserstein space. So recall, so what is the Wasserstein space? So I look into my underlying space is RD, and I look into probability measures on RD that have finite second moments. So what does this mean? These are Borel probability measures that have finite mean, finite variance, or in this case, because they're vector valued random variables, they have finite mean and finite covariance matrices. Now, if I have these curves on this P2 of RD, this P2 of RD, this is a metric space. And the metric is the W2 distance. Okay, so between any two probability measures, I have a metric, which is my Wasserstein 2 distance between these two probability measures. What did I do here? That this is, sorry. Okay, so this is the Wasserstein 2 distance between the two probability measures. That's my metric. Now, the goal towards which we were going here is that I want to understand this entire set of probability measures with finite second moments as first a metric space, but second and more importantly, a Riemannian manifold. Now, Riemannian manifolds are very, very nice. You can essentially do your Euclidean calculus on Riemannian manifold, but they need a lot of structure. And first thing that you would notice is that a set of probability measures cannot be finite dimensional. This simply doesn't make sense. It cannot be finite dimensional. And so whatever Riemannian manifold we're trying to construct must be necessarily infinite dimensional, which the theory becomes more formal. It's not quite a Riemannian manifold in the traditional sense, but we'll try to push this informal idea as much as possible. So here's a curve. If I want to define a Riemannian manifold, I need to talk about curves and derivatives of functions along those curves, right? That's my first two things. So I take a curve of probability measures rho t between 0 and 1 in P2 of RT. Okay, so that's my curve of probability measures. I can talk about when is this curve continuous? I can ask the question, when is this curve differentiable? And what is its gradient? What does it even mean? Now, continuity is a topological property. So that is easy. We have already talked about that in the metric space of the Wasserstein 2 metric, the natural topology is just weak convergence and the convergence of the first two moments. And therefore, that gives continuity. If I want to say there's a sequence of probability measures that converges to a limiting probability measure, all I have to argue is that the sequence converges in the weak sense, which is the integrals of all bounded continuous functions converge. I have to prove that the mean converges, the sequence of means converges, and I have to prove the sequence of covariance matrices converges in the Euclidean sense. That's it. That gives continuity. That's topology. The metric doesn't appear. It's differentiability. This is where the metric comes and plays a major role. How do I essentially define what is a gradient of such a curve of probability measures? Good. So we'll start with a simpler idea, which is coming from the general theory of analysis of metric spaces, and then we'll end the class with the idea of what is the right notion of gradient here. So the simpler idea is slightly stronger than continuous. It's the idea of absolutely continuous. So you might have heard this idea of absolute continuity for curves in Euclidean spaces. So in curves in Euclidean spaces, absolute continuity means that curves which have lengths, which have finite lengths. And so here is a definition. I say that this curve rho t is absolutely continuous, and I'm going to call this AC, if there exists some function g that is integrable such that the W2 distance between any two intermediate probability measures, rho s and rho t, is bounded above by the integral of gu from s to t. Right? So this is kind of measuring some sort of length. I have a curve in some space. I look into 2 points S and T, and I want to say that this is some kind of length. The length is finite. And that's what it is measuring. That there exists one single G that is integrable such that rho S and rho T, the W2 distance, is given by the integral of gu du from S to T. One thing, as you would notice from here, is that as S goes to T, this right-hand side, this goes to 0. Okay, so absolute continuity implies continuity. But there is more. In fact, if you can see from here that, say, for example, if G is bounded, let's say bounded by 1, then this curve is Lipschitz, which means that if G is bounded by 1, then the W2 distance between rho s and rho t is actually bounded by the difference between s and t. And with the curve, the curve of probability measures is Lipschitz. So absolute continuous curves are close to being the Lipschitz curve. You can turn one to the other by a time reparametrization, which is called arc length reparametrization. But absolute continuity is the notion that we are going to use. So again, let me reiterate what is our goal here. Our goal here is to somehow get get a notion of derivatives of this curve rho t. So along the curve, can I take a gradient? Is the definition clear? What is absolutely continuous curve? Okay, all right, okay. So moving on. So from abstract metric space theory, we can't get a notion of derivatives because general metric spaces don't allow derivatives of curves. But there is always a notion of what is called the norm of the derivative, and this is always very useful. So we we may not be able to define derivatives easily, but we can actually define norms of derivatives very easily. For any absolutely continuous curve, rho t, this is in a curve of probability measures, the following limit will exist almost surely. This is nothing but a generalization of what is called Rademacher's theorem in abstract metric spaces. So what does it say? It says that look at W2 distance between rho s and rho t, and you divide by the absolute value of s minus t, and you take the limit as s goes to t, then this limit should exist. This limit exists as a real number, as a non-negative real number, and that limit is my what I'm going to call rho prime t, absolute norm of rho prime t. It's easy to see why this limit would exist. As I said, this is basically a Rademacher's theorem. As I said, when you have a curve like this, W2 is integral of gu du, you're essentially asking for what is a Lipschitz property, because if G is bounded or you reparameterize time, you're essentially asking for a curve that is Lipschitz. Now, Rademacher's theorem would say that in Euclidean spaces, that Lipschitz functions are differentiable almost everywhere. But basically, the same proof works in the metric space. And a metric space, one can show that if you have some sort of Lipschitz property, which is this what absolute continuity over here is, then you can actually find this limit, and this limit will actually be less than gt. Okay, not very hard to believe, simply from this inequality that is here in the definition. That if I divide by absolute value of s minus t, the right-hand side clearly is less than or equal to g of t. Good. So if there is a derivative, and if there is a norm of this derivative, the norm of this derivative should be given by this metric derivative. And that's a nomenclature that is very common, that it's a metric derivative, but we don't know what the derivative is. We'll talk about this soon, but at least we can define what is a norm of the derivative. Good. Any questions? Okay, seems to start pretty abstract, but I'll give more examples. Follow the examples carefully. It's a pretty intuitive idea. Okay, but please interrupt me or ask questions if you feel lost. So let's see an example. As I have repeatedly said, one of the reasons why Bayesian analysis is so popular is that it lifts underlying Euclidean geometry to the geometry of the probability measures. So here is one. Let theta t be some absolutely continuous Euclidean curve in Rd. Okay, so some Euclidean curve which is absolutely continuous with respect to the Lebesgue measure in Rd. Let's do some cheating. Let's define rho t to be the delta mass at theta t. It's a probability measure. that puts mass 1 on my point theta t. Okay. Now, if I compute what is the W2 distance between two delta mass, well, it's of course the norm of A minus B, right? The 2 norm of A minus B, right? That's the only transport that you can think of is carry the entire mass from A to B. And so it's norm of A minus B. And so if I look into what is the W2 distance between rho t and rho s, that becomes the L2 norm of theta s minus theta t. I divide by s minus t. It should be an absolute value here. And I take the limit of s, if I take the limit of s to t, I get that this is the norm of the derivative of theta at time t. Right? So if theta is itself absolutely continuous, by usual Rademacher's theorem, a derivative will exist almost surely. And the norm of this derivative at whatever point it exists will also give the metric, this object, the metric derivative of the corresponding curve, which is the delta mass over theta t. Clear? Now, if you object that I'm cheating here because I'm doing delta mass, actually this is not a big deal because you can also take the normal distribution with mean theta t. I'm taking, okay, d equals to 1, but just take identity and solve the problem. So take normal theta t and variance 1. Now, even in this case, if I compute what is my W2 distance between two normal distributions with the same variance or same covariance, and just the mean is changing, as I have said multiple times, this is just a shift. You take the coordinates and you shift it. And so if you shift it, what you will get from here is that this would simply become the norm of the theta s minus theta t, and you'll get exactly the same answer. Good. And so the Euclidean geometry, the picture of the Euclidean geometry is somehow embedded in this picture in the Wasserstein geometry. Cool? Okay. How do I characterize absolutely continuous curves in the Wasserstein space? That's the main goal of today's lecture. So this is absolutely continuous. This is the definition of the absolutely continuous curve. I need to find curves which are slightly more than continuity. They're essentially Lipschitz. And why do I want Lipschitz? Because what I have in mind is to define some sense of derivatives or gradients of these curves. So I need some kind of Lipschitz property, at least, if not more. And so if I have this Lipschitz property, then I'm looking at curves which are called absolutely continuous. And I can't quite define what the derivative of the probability, the curve is. I can define what the metric derivative is. But how do I know that a given curve is actually absolutely continuous? If I have to compute the W2 distance between any two pairs, rho s and rho t, this seems like a very difficult task because computing Wasserstein two distances are not easy. Fortunately, there's a wonderful way of characterizing these absolutely continuous curves, and they are through PDEs. So let's see this PDE, or this family of partial differential equations called continuity equations. So what are continuity equations? These are solutions. These are PDEs on RD, which is my space. Time is 0, 1. And that satisfies the following PDE in the weak sense. That del t rho t plus this is the divergence. Okay, so this nablas dot, this is the divergence operator, which means that there's a vector valued function inside. You apply partial derivative to each of the coordinates and you add them up. Okay. What is this vector valued function that is inside? This is my vector, Vt. This is scalar, my rho t. So this Vt object, this is actually a vector valued function, which we are going to call a velocity field at time t. So let me repeat again. What is given to me is my vector valued velocity field Vt. What I'm looking for is a solution of the following PDE, which is del t rho t plus divergence of Vt rho t is equal to 0. And of course, I'll be given my initial condition rho 0. This will be given. Now, when I say that the PDE is satisfied in the weak sense, what I mean is that if you take a smooth, compactly supported function on Rd, and then if you apply this del t rho t over this integral psi x rho t of x, and then you take a partial derivative, then what you get here is that I would get the minus this divergence Vtx rho tx and this zeta of x. And then this object, when you do an integration by parts, becomes the gradient of zeta of x, Vt of x, rho t of x dx. And this should be in the sense of distributions on the interval 0, 1. So it doesn't have to have exact derivative at every point, but almost surely. Is this notion clear? So what is a continuity equation? It's a solution of a PDE. What is given in my PDE? What is given in my PDE is a vector-valued velocity field at every time and space and an initial point. And I'm trying to solve for the PDE del t rho t plus divergence Vt rho t is equal to 0. And this I can try to solve in the traditional sense if all derivatives exist and everything is smooth. But what I'm really looking for is in the weak sense. When I take some smooth test functions, apply those test functions, take those derivatives or integrate them, and everything works out fine. Okay, let's hear this. How are you guys feeling? Good? Okay. All right, okay. So this is my definition of continuity equation. So let's see some more examples. Let's take dimension d equals to 1. Take a constant velocity field. My Vt of x at any time t, at any space point x, is just 1. Now, I would look for my initial distribution to be standard normal 0, 1. And then I'm trying to solve del t rho t of x plus del x rho t of x is equal to 0. This is my continuity equation, right? Because if I take my velocity field vt to be exactly 1, then this just drops out. I'm in one dimension, so divergence operator is just the partial derivative with respect to x. And so I get del t rho t plus del x rho t is equal to 0. And that's what I'm looking for. Now, if you've never done PDE, you might wonder, how do I even solve this problem? This is not a very difficult PDE to solve at all. You can use any number of techniques. But I'll tell you what the solution is, and I'll tell you how I came up with the solution. The solution is that if you start from normal 0, 1, the solution is that rho t must be normal t1. So the mean is shifted to t, and the variance remains to 1. And this is just a density of the form e to the power minus x minus t squared over 2, where x is in the real line. But more importantly, the question is, how do I come up with the solution? How did I look into this and I came up with the solution? And that's where the important lesson of this class is. If you are somewhat familiar with PDEs, you'll recognize that this PDE is nothing but the transport equation. There's a reason why we call these to be velocities. Imagine that you have a bunch of particles on the real line where every particle is moving with unit velocity to its right. Okay, so I have a particle, this is my real line. I have a particle which starts with x0, and then after t amounts of time, it's at x0 plus t. So it's moving with unit velocity. And so if all the particles itself is random, or imagine that there are a bunch of particles which are shaped of a normal distribution. Every particle is shaped like a normal distribution. The histogram is that of a normal 0, 1. And every particle moves with unit velocity to the right. Well, after t amounts of time, all I have done is that I've sampled a random variable from normal 0, 1, and I'm looking into my new random variable xt, which is x0 plus t. But then what is x0 plus t? Well, it's normal t1, and therefore that must be the solution of this continuity equation. Good. So the continuity equation, let me repeat what I'm saying. The continuity equation, what is hiding is a particle's movement, a particle system moving, where the initial particle is chosen at random from the initial distribution rho zero. And now at time t, if the particle is at space x, it receives a velocity vt of x. And now you track this particle with time and you ask, what is its distribution at time t? Whatever the distribution is, that's a solution of the continuity equation. And this is an example that we see here. So I get x0 is normal 0, 1. My velocity is plus 1. So at unit velocity, it's moving to the right. So after time t, where is my x0? We said x0 plus t. And so if x0 is from normal 0, 1, what is the distribution of x0 plus t? Normal t comma 1. And therefore rho t, which is normal t comma 1, is a solution of this. And this you can verify directly. Just directly plug in rho t of x, plug in this formula, and check that this is actually a solution. All right. So that's the way that you think of continuity equations. So the same idea actually works in complete generality. So in complete generality, supposing that I have the following continuity equation, which is del t rho t plus divergence of vt rho t is equal to 0. This is my continuity equation in general. There is a general method in PDEs, which is called characteristic systems of ODEs, where you can solve PDEs by writing down ODEs. And this is an example of this. So what you imagine is that you have a bunch of particles at time 0. So t equals to 0. And the particle configuration is approximately rho 0. So in statistical parlance, the initial empirical distribution of the particles is close to rho 0, or if you want to be more precise, you sample IID particles from rho 0 at time t equals to 0. And now each of these particles is going to move according to this velocity field. So at each of these particles, at time 0, will feel a velocity v0 at its own position x. So maybe this guy moves here, maybe that guy moves here, maybe this guy moves here. So each one of these particles is feeling its own velocity field. And so at time t equals to, let's say t equals to 1, it will have a different configuration. Maybe something like this. And so you collect the histogram of these particles at time t equals to 1 and call that to be rho t. Now, reason I'm not quite using the word histogram because these are discrete objects and I really want something which is continuous. So all I'm saying is that sample the initial particle from rho 0. Now let it move according to the velocity field vt of x. Stop it at time t. Now look at the distribution of the particle xt. And that's what is going to be my solution, rho t. How do I check this? The checking is very easy. So again, imagine my particle system where xt dot is vt comma xt, where x0 has been sampled from rho 0. Now, if rho t is a law of xt, then I claim that it solves continuity equation. How do I check? So remember, I need to check the following. So let me go back to the definition. I need to check the following, that for every every compactly supported smooth test function, I need to check the following, which is that if I look into the integral of this test function with respect to rho t, and I take the time derivative of this object, then I should get the gradient of the function times the velocity vector vt integrated with respect to rho t dx. So this is like an inner product. Okay, so you should think of this as an inner product of gradient of psi and vt, and the inner product taken in the L2 inner product of rho t. So this is what I need to check. So let's verify this. I take some, this object is in CC infinity. I integrate with respect to ρt, and I take a derivative of this. But what is this in probabilistic language? This is nothing but the expected value of psi of xt. Sorry, of zeta of xt. So expected value of zeta of xt. So I take the derivative inside the expectation. Everything is smooth and compactly supported. I'm fine. Now, when I take this time derivative inside, then by chain rule, I get the gradient of zeta of xt and then x dot t. Well, what is x dot t? This is my velocity field v of t comma xt, which is my same as v of t comma xt, the same notation. And therefore, I guess this is the integral of the L2 inner product of the gradient of zeta and Vt of x with respect to rho t of x dx. And therefore, by my definition, it satisfies the continuity equation.
What is that V really saying? It seems totally general. Like it could be anything.
I'm sorry, can you repeat the question again?
I don't really is V x dot t equals VT xt. Is that giving it any structure? It seems totally general. Like it can be anything
This is
based on
totally
where it
general.
is.
It's just two different ways of looking into the solutions of continuity equations. And I'll come back to this point. This is what we called an Eulerian way of looking at things. And this is what is called a Lagrangian way of looking at things. So this is just two equivalent ways of looking at them. You can think of, so when I'm writing into curves in the Wasserstein space, I don't have a particle system in mind. All I have is that there's a curve of probability measures. But what this is saying is that you can always manufacture a particle system whose laws will give you that curve. These are just two equivalent ways of looking at the same object. What we will see later in this class is that there is no uniqueness in Lagrangian way. There are multiple ways, infinitely many ways you can come up with particle systems, but they will all give you the same Eulerian continuity equation. Okay, you should think of it as in some sense, like the couplings. I can pick a particle system that suits my purpose. Okay.
Okay.
All right. Okay. So here is the main result here, that all absolutely continuous curves in Wasserstein space is characterized by solutions of continuity equations. This is non-trivial because, again, what are absolutely continuous curves in the Wasserstein space? These are curves such that there exists some integrable function g such that W2 of rho t plus, if you remember this, the W2 distance between rho s and rho t is bounded above by the integral of g of u between s and t. That's the definition of absolutely continuous curves. This is hard to verify because we have to compute W2 distance between each one of them. It's just impossible task. But this you don't need to. All you need to show is that for some velocity curve, all you need to show is that for some velocity field where Vt is in L2 of rho t, it satisfies the continuity equation del t rho t plus divergence of Vt rho t is equal to 0. Okay, this is much easier because I just have to do some derivatives and integrals to solve this. In fact, so let's go over the statements carefully. So suppose my curve rho t is absolutely continuous, then there will exist some velocity field, which is in L2 of rho t, such that the continuity equation is satisfied. So that's one. But there is more. In fact, this velocity field can be chosen to be a very particular form. It must be almost of a gradient form. What do I mean by almost of a gradient form? It must be in the L2 closure of the gradient of g, where g is some smooth compactly supported function. So not necessarily Vt is of the form of a gradient of g for smooth compactly supported function, but there must exist a sequence of gn such that the gradient of gn will converge to Vt in L2 of rho t. So it's of a gradient form. Moreover, this must be true, that the L2 norm of this velocity field, when I integrate from 0 to 1, this must be finite. Conversely, if I have a solution of the following continuity equation, rho t vt solves continuity equation, and the integral of the L2 norm of vt from 0 to 1 is finite, then rho t is absolutely continuous. So this is a complete characterization of absolute continuity via this family of partial differential equations, which are well understood, which are called continuity equations. Let's go over it again. If I have an absolutely continuous curve, then for some velocity field, it must satisfy the continuity equation. But not velocity field is not even arbitrary. The velocity field is actually nice. The velocity field must be almost a gradient type. What does that mean? It means that there must be some sequence of Gn which are smooth, compactly supported, such that the gradient of Gn converges to the velocity field for L2 of rho t. And that the integral of norm of Vt L2 of rho t must be finite. And conversely, if you start with a continuity equation of this type, then the corresponding rho t must be absolutely continuous. Okay.
Excuse me,
We'll see more
Professor.
examples.
I have
Yeah,
a
go ahead.
question.
Yeah.
Um, so is this related at all to this? We can decompose the vector fields into like solenoidal and gradient vector fields.
That is exactly correct. And that's what, yeah, I'll come to this. In general, the velocity field is not unique, but this particular form of the gradient, this one is unique. And that's just a projection, as you have said, exactly.
Thank you.
Yeah. Any other questions? Okay, so this particular form of the velocity field, which is of the gradient type, is of utmost importance here. And this is what I'm going to call a tangent space. So if I'm given some rho, my rho is a probability measure in P2 of Rd. So it's in Warschatzky space. I'm going to define a tangent space. So what is my tangent space? It is some subspace in L2 of rho t. So this is L2 of rho. So this is a Hilbert space, right? L2 of rho is a Hilbert space with the usual L2 norm. In that Hilbert space, I'm going to create a subspace. What is the subspace? Well, look into the pre-closure. Look into this subspace which is not closed, which is the gradient of G, where G is compactly supported and smooth. This is some subspace of L2, but this is not closed. Take its closure in L2, and this subspace is what I'm going to call my tangent space. We carefully use the word tangent space because, again, we want to impose some kind of Riemannian manifold structure on the Warschatzky space. And the Riemannian manifold gives an idea of a tangent at every point, and that's where we're heading towards. So what is a tangent at a point, at a probability measure rho? Is a set of all L2 velocity fields which are in the closure of the gradients of smooth compactly supported functions. Okay. So the choice of the velocity, which satisfies this continuity equation, this is not unique unless you insist that the velocity is a tangent velocity. Then it becomes unique. In fact, for this particular choice of the velocity, where you impose the condition that the velocity is of the gradient type, it must be that the L2 norm of this velocity will coincide with the metric derivative. And this tangent velocity vector will be our notion of a gradient of a curve of probability measures. All right, let's recap from where we started. All right, so I'll recap these notions. This is the idea that we'll pursue. Let's recap. So where did we start from? We started from here. That I have a certain curve, rho t, in the space of all probability measures with finite second moment. I want to talk about this space of probability measures as some kind of nice Riemannian manifold. So I need, when is this curve continuous? When is this curve differentiable? Some notion of gradients, some notion of tangent spaces to define on this. Continuity is just weak convergence and convergence of first two moments. For differentiability, we introduce the idea of basically Lipschitz curves, or what we call absolutely continuous curves. So absolutely continuous curves are those where the W2 distance between any two points rho s and rho t is bounded by the integral of G. Once we do this, we have a notion of metric derivative, which is that this W2 distance, pairwise W2 distance, which is just non-negative numbers, they are differentiable, and it gives me this notion of rho t. And this should be our norm of the derivative, which means whatever notion of derivative and its norm and some kind of metric tensor that we define on the tangent space, if I take the gradient, if I apply the metric tensor, I must get the metric derivative, which is rho prime of t. And that's what we essentially get. And then we talk about continuity equations. Continuity equations are solutions of this type. I'm given a velocity field vt, and I'm solved for del t rho t plus divergence of vt rho t is equal to 0. That's the PD that I need to solve. Then I talked about that how these continuity equations can be seen in a Lagrangian point of view by thinking about particle systems where the particles are moving according to the velocity field. And as the particles are moving according to the velocity field, if I look into how the law of a random particle is moving, then that's what is tracking the continuity equation. And that's a very natural way of thinking about continuity equations. And then we have the main theorem here, which is that says that a curve is absolutely continuous if and only if it solves the continuity equation. And then if it solves the continuity equation, there are many, many velocities that will solve the same continuity equation. But there is one that is special. That one is the one which is of the gradient type. Or in other words, this lies in the particular subspace of L2 of rho t, which is given by the closure of the gradient of smooth compactly supported functions. So we pick out this subspace, and we say that that's what is going to call my tangent space. And any vector valued function that lies in this tangent space is what I'm going to call my tangent velocity. This, when you impose the velocity must be in the tangent velocity, then the continuity equation, then the absolutely continuous curve will give you a unique velocity. And that unique velocity, rather, what I should say is almost surely unique velocity. And that unique velocity will satisfy my condition that the L2 norm is given by the metric derivative. And so if I think of my Wasserstein space as some manifold, and if rho is a point here, what I've essentially created is some kind of tangent space and a notion of a metric derivative, a vector in this tangent, and a metric tensor in this tangent space. Everything is infinite dimensional. So the manifold is a space of probability measures. The tangent space is a subspace of its L2 functions, are the vector valued L2 functions. And the metric tensor on this tangent space is given by the L2 norm. Okay, this is a theme that we will do over and over again as we move on with this course. Do you want me to repeat something here? All right. Okay, good. Let's do more examples. Here's an example. Anybody who has taken basic probability who should be familiar with exponential distributions. So let's take rho t to be the exponential distribution with the rate 1 plus t. So t is between 0 and 1. So it starts with exponential at rate 1 and ends with exponential with rate 2. We know what is the density function. The density function is 1 plus t to the power minus 1 plus tx for x non-negative. And this is 0. The density is going to be 0 when x is negative. Good. This rho t seems particularly nice. It's exponential of 1 plus t. It's clearly continuous. Okay, can we show that this is an absolutely continuous, can we show that this is absolutely continuous curve? To figure out whether this is an absolutely continuous curve, your job will be to come up with a particle system where if the initial particle is sampled from exponential 1 and it moves along a smooth velocity field, then at time t, the distribution of this particle should be exponential of 1 plus t. So I'm asking you to create a stochastic process where the initial particle is moving along some smooth velocity field. And so if you start the initial particle at exponential 1, at time t, you're at exponential 1 plus t. Is the challenge clear? If you can do this, and if the velocity is integrable and so on, then this is absolutely continuous. Good. Let's see, how would I do this? Well, as it is well known, if I take x to be exponential 1 and a to be some positive number, then x over a is exponential with rate a. Okay. Again, basic facts about exponential distribution. If you're not familiar with it, just do your change of variable here. Do your change of variable here and verify this, that this is actually true. That exponential is what is called a scale family. If you divide x by a, you get exponential a. So it makes sense that if I take my x0 from exponential with rate 1, and if I define xt to be x0 over 1 plus t, well then xt clearly is exponential 1 plus t. But that gives me some trajectories. At every time t, my initial point x0 is simply being scaled down by 1 plus t. What is the velocity of this trajectory? This is the time derivative of the paths, and that's minus xt over 1 plus t, because if I take a derivative here, I get minus x0 over 1 plus t squared, but x0 over 1 plus t is xt, and so this is minus xt over 1 plus t. So my vt of x, my velocity field, is nothing but minus x over 1 plus t. Clear? Is this of the gradient type? You bet it is, because this is an affine function. And so, of course, this is gradient type. This is an affine function. And so this is of the gradient type. So it's in the tangent space. Is it also, we also need to check this is in the L2 space, which means is the L2 norm of the of Vt finite? Well, exponentials are well known to have all finite moments. So of course, it's also in L2 of rho t. So I have a gradient type, which is in L2. Therefore, this is my tangent velocity. You can verify that the integral of the norm of the L2 norm of the Vt from 0 to 1 is finite, which will tell you that this is actually absolutely continuous. Is this example clear? Because these are one-dimensional distributions, I can also exactly compute its Wasserstein 2 distance and verify what the metric derivative is. But this is so much cleaner, so much more clear to do this. All I'm doing is just creating a stochastic process where my initial distribution is x0, and at every time t, I recover rho t. And the stochastic process has smooth paths. It has paths which are differentiable. And if I pick a derivative that's of the gradient type, and is square integrable, and I have my tangent velocity. Cool? All right, okay. I want you to think
May I
what
ask a question?
Yes, please go ahead.
So the tangent space here is the closure of gradient types.
Closures
But
of gradients of smooth compactly supported functions, but the closure is with respect to the measure where you are computing the tangent space.
yes. In usual like finite dimensional Riemannian geometry, I'm used to the gradient being quite different from the tangent space though, because usually the gradient is like dual to a differential form, not like elements of the tangent space itself. And those are like derivations or like directional derivatives, not gradients.
Yes, so I'm being loose with some of these ideas. You should really call it directional derivatives here
Oh, okay.
because, well, if you look, this is already here. Essentially, you look into this how the velocity is working on the smooth functions is of this type, this gradient of psi times velocities here. But yes, I'm sorry, I'm being a bit fast and loose with language here. The idea is that if I have a curve, then along that curve I have a directional derivative, and that's the velocity field. It
Okay.
depends on the whole
Okay.
curve. Yes.
Okay, thank you.
Okay. If you understand this particular example, then try thinking about this following example. Rho t is exponential with rate t, and now t is between 0 and 1, but 0 is not included. Can anyone tell me what is the problem at t equals to 0?
VT wouldn't be integrable.
Well, rho 0 actually does not
Well,
even
maybe it would
exist.
almost surely.
Yeah, rho 0 doesn't even exist here because exponential at rate 0 doesn't even exist. That's just a Lebesgue measure. It just, it doesn't exist. But that's not a problem. The curve will exist for every epsilon to 1 for arbitrarily small epsilon. And the definition actually does not depend on the 1.0. In fact, everything that we do, you can drop a set of measure zero time points. So everything is still fine. You just have to be careful in defining what the particle system is.
Excuse me, Professor.
Yeah,
About this example, so when we change the domain of time to be 0 to 1,
yeah.
you would think that intuitively you could find a limit as t approaches 0 of a Dirac mass at the origin, like just
It is not
intuitively
the Dirac
speaking.
mass at the origin. Exponential with rate 0 becomes more and more flat. The expected value of an exponential lambda is 1 over
Oh,
lambda. It
okay,
just
okay,
becomes
sorry.
Lebesgue measure
Okay,
on the half-line.
okay, thank you.
It's not the Dirac mass.
Okay, sorry, I was thinking about the wrong thing.
Yeah, that's fine. Any other questions? Okay, good. Let's try one more example here. So here we consider a fundamental example, which is the heat flow. So the heat flow, as I've written in the probabilistic form, Young might use the more analytical version of it without the half. It's a solution of the following PDE. Del T rho t is 1/2 Laplacian of rho t. So this is my Laplacian operator, which is the second derivative with respect to each of these coordinates and added them up. Now, the heat flow, this very, very well known and well studied PDE, is actually also a continuity equation. How do I see this? Well, you can look into the Laplacian of rho t and see that the Laplacian of rho t is nothing but the divergence applied to the gradient of log rho t times rho t. Why? Because when I take the gradient of log rho t, I get this is the gradient of rho t divided by rho t. And this rho t in the denominator will cancel with the rho t in the numerator. And then I'll be left with the divergence of the gradient of rho t, which is, of course, just a Laplacian. Right? So the Laplacian is of the form divergence of some function, which is this object here. So I'm going to call, so remember what I want to write is del t rho t is equal to a minus gradient of Vt rho t. Not the gradient, the divergence of Vt rho t. So that's my continuity equation. The minus sign is a convention comes from the particle system. And so if I compare this form with this particular form, you see that if I pick my Vt of x to be minus 1/2 gradient of log rho t of x, then I recover my continuity equation. This continuity equation is of the gradient type. In fact, it's the gradient of the log of rho t. I want you to understand something interesting here. So imagine that you have this particle system, which is tracking this velocity field. If you have a bunch of particles that are following this velocity field. But in order to proceed, the velocity field itself depends on the configurations of the particles. So as opposed to the previous examples that I covered, in the case of Gaussians, in case of exponentials, if I'm at time t, the particle doesn't care about all the other particles. It just looks into where it started from and determines where it needs to go into the future. This is different. This is an example of what is called a mean field interaction, where the particle, in order to move into the future, must know the configuration of all the other particles. It must calculate rho t itself, then take log, then take gradient, then take negative 1/2, apply the gradient at its current position to figure out where it should move next. Nevertheless, this is a gradient type. So this is an example of what is called a mean field interaction. So the particles are interacting with each other. To know where a single particle moves into the future, you must know the position of all the other particles. What is the L2 norm of this velocity? This is also a very important object. If I calculate what is the L2 norm of this velocity, I get this is 1/4 the gradient of the log of rho t norm square rho t dx. And this is this particular object, which is this gradient of log rho t L2 norm of this object, L2 norm square of this object. You can also write it in this way. Gradient of log rho t is gradient of rho t over rho t. The square cancels with rho t, and this is what remains. And this is what is called the Fisher information. Okay, very, very important object, comes up in all these analysis. It's called the Fisher information. We'll see this very often. So when is this absolutely continuous? When the integral of the square root of this Fisher information from time 0 to 1, this is going to be finite, then this solution of the heat flow is also going to be an absolutely continuous curve on the Warschachian space. Good. Okay, we go back to the lack of uniqueness. By the way, is this example clear? So we go back to the lack of uniqueness of this velocity field. For an absolutely continuous curve, the velocity field is not unique unless it's a tangent velocity. And we have talked about this a bit. Let's look into this absolutely continuous curve. So it's a solution of del t rho t is the divergence of vt rho t is equal to 0. That's the PDE that I'm trying to solve. The solution that I'm interested in is my space of is a family of probability measures rho t. I would get the same solution if I replace my Vt with Wt, which solves the following zero flux condition that the divergence of Wt minus Vt rho t is equal to 0. Okay. And that's clear. If I have any other Wt, it will of course give me the same solution, because if I just plug in the difference between the two, the difference between the two is going to be 0. Now, what is the space of all velocity fields, vector valued fields, that satisfies the difference between these two rho t divergences is 0? Well, this is a linear constraint, and therefore this is a whole vector space. It's an entire infinite dimensional vector space of possible velocities. We just have to impose that they are in L2, so it's some subspace of L2. There is no uniqueness. Any element of this vector space, you can plug that as a velocity, and you can still get the same solution of the continuity equation. In fact, the concept of velocities may not even exist. And this is one of the things that we just saw here. Go back here. Look at the heat flow. This is a solution. Del T rho t is 1/2 divergence of Laplacian of rho t. And we just figured out that is given by this gradient, this tangent velocity, negative 1/2 gradient of log rho t of x. But if you're coming from a probability or statistics background, this is not how you think about heat flow. The way that you think of heat flow is that you run a Brownian motion So you start your Brownian particle, x0, from some initial distribution, rho 0, let's say here, and then you let your Brownian motion run. And this Brownian motion at time t, you look into its position xt, and that has distribution rho t. This is how you construct the solutions of heat flow. If you're unfamiliar with Brownian motion, then we can't go into depth of Brownian motions here, but this is an important concept that will come up here over and over again. So Brownian motion you should think of as like a continuum approximation of what is a random walk, a simple symmetric random walk. So if you could zoom in infinitely, you would basically see a random walk behavior where every step you go up or down with probability 1/2 or 1/2. Now, this zigzaggy curve of Brownian motion is another Lagrangian description of the same Eulerian system, but Brownian motion is well known not to have derivatives anywhere. X dot t, this never exists, does not exist. So one can create particle systems which are so rough. Brownian motion is Hölder continuous for Hölder coefficients less than half. It's so rough that the concept of velocity does not exist. And yet, if you look into its law, you get back the solution of the continuity equation. But there will exist some other particle system where this velocity is smooth, it is of the gradient type, for which the same system of laws will be achieved, but the particle path, the trajectories of those particles is not going to be Brownian motion. Is that clear? Another way to think about it is that the Brownian particles, they're not mean field. They don't even have velocities. They don't care about where other particles are. They are just moving on their own randomly. But these particles are mean field. Their trajectory depends on the position of all the other particles, and so they must carefully pick where everybody else is. How are you guys feeling? Okay? Right? Okay. So as I'm saying, there can be infinitely many stochastic systems where the particles are moving, and what is called the marginal distribution of the stochastic process solves the continuity equations. I would say here that it's a marginal distributions of the stochastic process solves the continuity equation. But the joint distributions can be arbitrary. They can be completely different. The joint distributions of two-point joint distributions of Brownian motion is completely different than the joint distribution of this particle system, which has smooth velocity fields. So it only tracks the marginal distributions. Nevertheless, as I said, as I keep on saying, that tangent velocities are unique. And as one of you already mentioned, that this is nothing but a projection. And so let's review that fact that the tangent velocity is essentially a projection. It's the minimum L2 norm among all possible velocities. So therefore, this is unique. So this is my, if I take my rho, my tangent space at rho is the closure in L2 of the gradient of G in smooth compactly supported. And so a vector valued field is in the tangent space if and only if I look into the L2 norm of this object, this is the smallest among all possible L2 norms of the solutions of the zero flux condition, which will give the same continuity equation, that the divergence of W minus V rho is equal to 0. All right, good. So the set of solutions of velocities is very large, but the tangent velocities are the projections, and there's only one, which is minimizes the L2 norm. You might wonder, why do we care about other velocities? Because sometimes they're useful. I had mentioned linearized optimal transport before. We'll see, for example, linearized optimal transport. If you do, you get other velocities, and sometimes they're useful. A tangent velocity may not be always very useful. Okay, I keep on talking about tangent and tangent velocities. So one of the properties of tangents in Euclidean space is tangential approximation. So in Euclidean space, if I have a curve in, let's say, R, a smooth curve, I have the following property, which is that if I look at a time t, I look into this curve x of t, and I'll draw its tangent. Then at a small enough time point t plus h, the value of the curve, which is xt plus h, is very close to what the value of the tangent is. And what is the value of the tangent here? The value of the tangent is xt plus h times the velocity, the v vector that we get from this tangent, the slope. Right? Everybody agrees with this? This is one of the main properties of smooth functions, that if I have a smooth enough function, I would be able to approximate the smooth function by piecewise linear functions by taking the slope of the tangent and just moving along the tangent. If you want a more physical interpretation, I move along with a constant velocity of the tangent for time h, and then I change my velocity. Then I do my acceleration. Then I again move by a constant velocity, and then again do my acceleration. And by doing this, I would be essentially tracing out the same path as by constantly accelerating. Remarkably, the same thing is actually true for Washington spaces as well, except everything has to be lifted to the space of probability measures. And this theorem, which you can actually find in the textbook of Ambrosio Gili Savary, is very useful. So what it says is the following. So I look into my absolutely continuous curve rho t and vt, where vt is picked to be my tangent velocity. So no arbitrary velocity, specifically the tangent velocity. Now I look into time t, and I look into time t plus h. At time t plus h, I have my curve, which is at rho t plus h. This is my probability distribution at rho t plus h. Now, what I do at time t is that I push forward my time t measure by the map, which is identity plus h times vt. Okay, so what does that mean? Is that if xt has rho t, the law, then I look into the law of xt plus h times vt xt. Okay, and I call this to be, the law of this is what I call rho t plus h hat. And what this theorem is saying is that W2 distance between rho t plus h and rho t plus h hat, this estimate, is little o of h. So when you divide by h and you take h going to 0, almost everywhere you get 0. Again, what you see here is how Wasserstein geometry is lifting Euclidean geometry to the space of probability distributions. The idea is that their underlying system is basically particles. Particles creating their own smooth curves in RD. And if for the particles I can do a tangential approximation to their curves by tangent, then I should expect that the same idea should be lifted to their probability measures by simply replacing this tangential movement by a push forward.
I have a question.
Yes.
This is a very nice result. I'd like to know if this type of result, or more generally what we're doing, how dependent is this on the quadratic cost, or are there other cost functions where we're still going to get these types of nice results?
Unfortunately, quadratic cost is the one where you get all these nice results. For other results, for peak cost, you get some of them, not all of them. But yeah, most of the nice results, as we are seeing in this Riemannian structure, you get it for even like the definition of tangent cones for other Wasserstein peak cost becomes much more complicated. So there's something about the quadratic cost which is very useful. There are other structures, which is we will talk about this towards the end of the quarter here, where you can deform. You basically start with the quadratic cost and this geometry, but then you deform it somehow, and they also will preserve all these properties. but not when you change the cost function. If you change the cost function, things can go bad. So some things will be true, but this particular one, as far as I remember, maybe it holds for WP cost as well, but even the definition of tangent becomes complicated.
Okay, thank you.
Okay. Any other questions? Okay, so this is the idea of why we call it a tangent, because if you move along your particles along these tangent velocities, you recover the law at a close enough time point. Right, so basically this is I don't need to spend time on this. That's what I said, that this velocity Vt, this is an Eulerian description. All these ideas there are many different fields have contributed ideas to optimal transport. So these ideas are coming from fluid mechanics. And if you have a fluid mechanics, the idea is that if you have, let's say, a river which is flowing, so imagine that a river that's flowing. If you drop a leaf at the river here, and you look at how the leaf is traveling along the river, maybe it's circling, maybe it's moving this way, and maybe it's moving along the flow, then the behavior of this leaf is a Lagrangian trajectory. So that's a Lagrangian trajectory. But so if you're an ant and you're on the leaf and you're traveling with the leaf, you are tracking the Lagrangian trajectory. On the other hand, if you're a human and if you're at the bank of the river, and if you're measuring along the bank, what is the velocity of every point in space at that particular time, then what you're doing is an Eulerian point of view. So you're looking into this Vt of x and rho t of x at every time and every space point. So that's your Eulerian point of view. But if you're following a particular trajectory as an ant on the leaf, then it's Lagrangian. Infinitely many Lagrangian trajectories gives the same Eulerian velocity. If you're from a person from stochastic processes, this is just another way of saying that infinitely many stochastic processes will give you the same marginal family of distributions, or same family of marginal distributions. The joint distributions will be different, but the marginals are always the same.
It wasn't clear here what is the joint and what is the marginal.
I'm sorry?
What is the joint and what is the marginal? When
So
you
over
were
here,
saying
if
that
you
with the
look
continuity
into
equation.
the continuity equation has no joint. The continuity equation simply has absolutely no joint distribution. So here, for example, if you look this particular example, in the heat flow, if I start with, let's say, rho 0 to be, let's say, normal 0, 1, and if I take dimension d equals to 1, then I can take rho t is normal 0, 1 plus t. That's marginal. If I start my Brownian motion from standard normal, and if I measure its law at time t, then I would get this marginal. Now, if I take my Brownian motion at time 1/2 and at time 1, and I look into the joint distribution of b1/2 comma b1, that is a joint distribution of two Brownian particles. That has no analog in continuity equations. Continuity equations is simply saying how the marginal distributions are evolving. It says nothing about joint distributions at a long time. Does it make clear?
Well, I've been thinking about these particles like samples and running samplers. So these joint is in between different time
Correct.
points of one
If you are a
sample
time series data,
or
then
different
that would give you
samples.
joints. Correct. So you would get a joint distribution if you are tracking it along time points. If you measure the stock price today and if you measure the stock price tomorrow and you find what
Of
is
the
the
same
correlation
particle.
between them, yeah, same stocks,
Okay.
then you would get a joint.
Okay, got
But
it.
there's no way to recover that from continuity equations. Continuity equations are only about marginals.
Got it.
Okay. So that's why there are infinitely many stochastic processes which will have different joint distributions, but will have the same flow of marginal distributions. So I'll end with this following example here, which is about Ornstein-Uhlenbeck diffusion. So this is again a very, very well-known diffusion that is studied in lots of places. So in Ornstein-Uhlenbeck diffusion satisfies the following SDE, which is dxt is minus 1/2 xt dt plus Brownian motion dbt. SDE, these are parts are the same as Brownian motion, so this is non-differentiable. But it has its own flow of marginal distributions, and that set of marginal distributions is indeed absolutely continuous. But this is not the right marginal velocity, the tangential velocity. So how can I find out what is the correct tangent velocity for the marginal distributions that is generated by Einstein-Uhlenbeck? We can do this by what is called Ito's rule or Dynkin's formula. And next time I might go a little bit over the thing, but just bear with me now. If you know something about stochastic differential equations or diffusions, you know that it comes with something called a generator. And the generator of Einstein-Uhlenbeck is a differential operator which looks like this. It's minus 1/2 x dot gradient of zeta. Zeta is a smooth test function, plus 1/2 Laplacian of zeta. So if I want to figure out what is the right continuity equation, I will plug in a test function. I will apply the partial derivative with respect to t, and that gives us del t, expected value of zeta of xt. Ito's rule or Dynkin's formula tells me that this is the expected value of the generator applied to zeta applied to xt. And so if you look into this object, the expectation of this thing, this is nothing but this object. The generator is given by minus x inner product with the gradient plus Laplacian, and the law of xt is rho t, and so you integrate with respect to this. Now this is already of the gradient form, the gradient of zt, so that's fine. I need to transfer this gradient, and so I'll do one integration by parts, and I write it in this particular form. And remember, to solve for continuity equation, the velocity, it looks like this. For every smooth test function, I should have, this is the gradient of zeta dot velocity rho t. So it's an inner product of the gradient and the velocity. And so if I pull out all this gradient of zeta term outside, I recover that this velocity is this, minus x over 2 minus 1/2 gradient of log rho t, which is of the gradient form. It's a gradient form of this type, norm x squared over 2 plus log rho t. And therefore, this is also the tangent velocity as long as some kind of Fisher information kind of constraint is satisfied. Okay, so that's my final example here. And so I'll stop here, and next time we'll talk about the Benamo-Brenier formula. Okay, any questions?
How do we know if we can just like use a ODE with rho, since like for instance the transport equation, it's often used for systems that conserve mass, so it seems like a good fit there. But how do we know if when we just write down some ODE, it's going to the probability is going to be conserved?
No. So this is why you raised a very important point. The reason we get continuity equations is exactly because this is a flow of probabilities, and therefore the total mass, which is 1, is preserved. So the way to think about is that, if you have these particles moving around, the total mass always has to be 1. So there's always this condition that the amount of mass that exits, amount of mass that enters must be the same. And so that's exactly what is forcing continuity equations. So that's why the transport equation is relevant. So if you write down an ODE and it does not preserve mass, then your mass is escaping. Then it cannot be a flow of probability measures.
Okay. Yeah, so we sort of have to know beforehand this ODE is known to conserve this quantity.
Yes,
So,
but in this case,
yeah.
you don't, because you already know the full characterization, that it must be of the type of continuity equations. So you already know this. So I would invite you to take your favorite stochastic process, take its marginal distributions, try to solve for the tangent velocities, and see how your intuition is very different from how the stochastic process behaves. Like again, as I said, Einstein-Uhlenbeck is not a smooth path. It's Brownian motion with some drift, which is this. If it goes very high, it gets pulled towards the zero. If it gets very low, it gets pulled upward to a zero. This is the characteristic way of thinking about Einstein-Uhlenbeck as a negative feedback loop. But that's not the velocity what Wasserstein space is giving you. The Wasserstein space is giving you this velocity, which is this term, which may not mean much to you right now, But soon we will interpret this velocity as an entirely different object, as a gradient of a Kullback-Leibler, or a negative gradient of Kullback-Leibler with respect to the stationary distribution. And so it's a very different notion of what velocity is. And you should be comfortable going back and forth between the stochastic picture and the geometric picture.
Okay.
Okay.
I have a couple questions.
Yeah.
First of all, when we look, I'm not too familiar with like Ito's or the stochastic calculus side of things. So if I look at this SDE on the previous slide here, can we think about the generator as corresponding to the Green's kernel for the corresponding like PDE of the laws of these random variables?
Think of the grid generator as the Green's kernel.
For
I mean,
example,
they
like
are
the
related, but it's not quite like that. The generator is essentially defined in this way, that if you look into expected value of some test function zeta of xt, and you subtract off the expected value of some, or rather, okay. If you look into, this is the definition of the generator, the conditional expected value of zeta of xt minus zeta of x0, and you divide by t, and you take the limit as t goes down to 0. This is the generator L zeta at x0. So it's a property of the joint distribution at 2 points. You look into the conditional expectation of zeta applied to xt given where you started. Now, as t goes to 0, these stochastic processes have continuous paths. So zeta of xt converges to zeta of x0. And now if you take a derivative given time t, you would get the generator of zeta at x0. This is how you think about it. So it really comes from 2-point joint distributions of a diffusion.
Okay, thank you. And then my other question is when we were looking at the example of the exponential family,
The
I guess I
exponential
was,
distribution, you mean, not the family,
yeah,
exponential
sorry,
density.
the exponential density.
Mhm.
If we were to consider this curve going from time 1 to infinity, let's say,
Mhm.
could we say that in some rigorous way, like the limit as we approach infinity would be a Dirac mass at the origin?
Yeah,
Could we
because
use,
that's continuity. That you don't, all you are basically claiming is that if the limit as lambda goes to infinity of exponential of lambda is Dirac mass at 0. But this is a statement about weak convergence. So
okay.
all you have to do is that, does it converge weakly, and do this, the first two moments converge? And the answer would be yes. But this is not using the Wasserstein 2 metric. Continuity is a weaker property.
Oh, okay, so we need to also check the convergence of the moments to get
Right. So you
this.
have to talk about
Okay.
convergence of moments. So the right. So
Okay.
as I said, in the exponential lambda, you can easily verify that both the moments will also converge, and this weak convergence will also hold.
Okay, thank you. That's very helpful. My last question is with this heat equation, I
Yeah.
guess when we discussed this mean field interaction property,
Mhm.
to me, like I'm coming from physics, and it
Mhm.
seems like this would violate the principle of locality. And so it seems difficult for this to be like physically meaningful. So can you just speak, is there like a stochastic side to this which makes it more physically meaningful?
I'm
Um,
not sure why principle violates any of that. I mean, this is a mean field equation. Later in the course, we'll write down explicit particle system. So here is the particle system, which is mean field equation. Um, So take, for example, let's say a particle system is moving this way, where everybody is attracting everybody else. So I would say that dxt is equal to, let's say, so the ith particle at time t, the ith particle at time t, let's say, is xtg minus xti averaged over g, um, let's say 1 over n. So the way that so this is ddt basically. So what is happening here? What is happening here is that the ith particle, the way it moves, is that if there is a particle, this is in d equals to 1. If there's a particle which is above it, it gives it a positive velocity. If a particle is below it, it gives a negative velocity. And the total velocity is whatever it is, the sum total of all velocities of all of them. Now, this is in d equals to 1, but this is exactly how gravitational field will work in d equals to 3. If you have a particle moving through space, it is feeling gravity from every other mass in this universe, and some kind of averaging over the mass is essentially determining how it's moving through space. So I don't see how it violates any physical principle.
I guess like when I'm thinking of when you mentioned that you could view the heat flow in two ways. First, you have like this deterministic flow where
Mhm.
the deterministic flow cares about the position of all like the full distribution.
Right,
But then we could also view it from a Brownian side where
right,
from where the particles actually don't care
right,
about
right,
the position of all other particles.
right.
Uh,
So the Brownian side is the actual physical one, and that's why it came from physics. The deterministic flow has no physical interpretation as far as I know. This is clear, this is just a figment of this geometric technology that we are developing. But it's not that this is like when you, if you think about heat flow as like molecules vibrating when you, as you pump in heat, the molecules don't give a damn about all the positions of other molecules. They're just happily vibrating just like Brownian motion would. And so this is my point that if you follow the trajectories of molecules, then that would give you just like Brownian motion. But this is another set of movement, which is smooth, has no physical interpretation, which will generate the same flow. Okay,
Thank you. That's very helpful.
good. If there are no other questions, okay, so I'll end it then. All
Is
right,
there a
okay, so
good
you got it.
resource for looking at this Ito's formula? Basically this
Right, so it is formula you can find in any of the standard stochastic analysis textbooks, or I mean, in Wikipedia probably has a good enough description right now. I mean, it's such
okay.
an important result.
Sure. Okay. Thank you.
All right, okay.
Sorry, there's a question.
Yeah, go ahead.
What's the like? Where do I look? What's the source of all the material covered today? Where can I find it?